or most NP-hard problems are not NP-hard in a random sample. And we don't even get random samples, we get highly structured samples. So let's not be scared about let's not be scared away by the NP hardness of some of these problems in perhaps 2% of the cases. We can solve them in 98% of the cases, we're all fine. All right, so challenge number 0, really, really easy. Given an executable, reconstruct the set of possible return values for each function. That's actually not really a challenge, that's why it's got the number 0. You can do that in a bunch of Python script in about 2 days. But it's surprisingly effective in helping your program understanding if you see a function and your disassembler is telling you, okay, now this function you can return -1, +1, and 0. And that just smells like a comparator. Or this function here can return 0, -1, or malloc, and that just, or the return value of malloc. That just smells like something that's allocating something and giving me an error, if not. Or you automatically extract all the error keys from Microsoft code, like when they return C00053, C0054, 800022, and so forth. So that is really, really easy in almost, in more than 50% of all cases. Gets a little bit more tricky in others. Not really a challenge, not really that interesting. Let's start with something interesting. Full executable data structure reconstruction. Given an executable, reconstruct all data structures used in the executable. Step 1. Secondly, reconstruct nesting of data structures where you can recover it from the executable code. Thirdly, reconstruct points-to relations between data structure members and data structures, meaning if structure member 5 points to another structure, record that. Then construct a graph from these relations, meaning you have a graph where every node is a data structure. Whenever one data structure refers to another, like a data structure member refers to another data structure, add an edge to this graph. Now, this graph should not only help you greatly in understanding how data structures are correlated. I mean, we all know this from code auditing when you look at okay, now they're taking this structure and this pointer and that pointer, and then in that structure they're dereferencing and dereferencing, and you surf through header files for 5 minutes just in order to find out what the final type of the thing is you're looking at. And that would just be solved if you had a diagram like this. Secondly, in that diagram, you could very easily recover recursive data structures like trees and graphs and so forth. So, yeah, and I don't think it's all that difficult. I'm very, very sure that this is doable. I'm very sure that this is doable with, let's say, 2 man-months worth of work. I even have a suggestion for a pseudo algorithm. I don't know whether that'll work. That's really totally pulled out of my ear. And I don't think, well, I'll just try to explain how I would go about this now. Thing with research is you always run into problems, like you always have an idea of how something works, and then you try it, and you get a bloody nose, and you have to rethink it again. So the idea in this case is you take every function in the executable and you iterate over them. Now, for every memory access in that function, you associate those memory accesses that operate on the same data block, like on the same memory region. And then you create a data structure for each of these regions with these offsets in the function. Then, after you've done that, you iterate over all functions again and build argument prototypes for these functions, saying, now this function takes as first argument the data structure number 1. Takes as second argument the data structure which we've assigned number 2 within this function. Once you've done that, you do a next round where you merge basically all the information. If you know that this function here has a data structure with number 20, which passes on to this function over here as data structure number 25, you merge these 2 data structures. And you iterate over that, and because you're essentially iterating over the call tree, you should terminate in n half steps, where n is the maximum depth of the call tree. In theory. I haven't tried this, so careful. Well, creating the graph from these data structures should then be relatively easy, because you just iterate over the data structures and iterate over the locations where they're being written to, and check whether they're writing a pointer to another data structure. Should definitely be doable as well. All right, so that was number 1. Challenge number 2. Well, we all know and we all hate object-oriented code. And we mainly hate it because our tools are not adequate. I mean, seriously, doing disassembly of object-oriented code with our current infrastructure is a bit like having to dig holes with chopsticks. You just know it's not the right tool for this. You have all this indirection, you have indirect method calls which you can't easily resolve yet, and so forth. So, challenge would be, given an executable, reconstruct all the classes, like recover all the constructors to classes, from these constructors, reconstruct the class. From the calls to relationship between constructors, you can infer inheritance relationships, which means if I inherit or I derive a class from another class, obviously I'm calling the superclass's constructor. Once you've reconstructed all the data structures and their inheritance relationships, you create UML diagrams from the classes. So by next year, this time, I would like to have something that creates me a UML diagram from a given object-oriented piece of code as executable. Yeah, and then you can merge the UML diagram, which we generate, with the type info diagram generated in challenge 1. And that should go a very long way. I actually think this might be a little bit easier than challenge number 1, because you get a lot more structure in C++ code than in regular C code. And if you're a little bit weenie, you can fall back to being compiler specific. But I think this should also be not, I'm not saying easy, but not too difficult. All right, yeah. The grouping of functions towards these classes, of course, like once you recover the classes, not once you recover the classes, but part of recovery of classes is, of course, recovering all their methods. And you get a whole bunch of methods from the vtables of the class immediately. And then you have to sort out which methods belong where, because you can't just take the vtable and transcend downwards in the call tree and say everything here belongs to that class, just because there might be methods belonging to multiple classes. But in general, this should be, like, one should be able to sort this out. To find methods that are not virtual in nature might be a little bit more tricky, because you might have to actually have a relatively strong data flow algorithm to do this. I don't know, this might be a little bit difficult. A really, really trivial but fun thing to do once you're done, because you have the data structure layout and the type info for the classes, and you have the vtable pointer, you can scan through memory and look for the vtable pointer. Whenever you see it, well, you have a class instance. So you can runtime, enumerate, and edit C++ objects in memory. I think those of you that like World of Warcraft and those sort of games are just drooling over the idea. So that should work. Okay. I talked about this before, challenge number 3. Automatically decompose an executable into modules. The modules should reflect or exhibit loose coupling and strong cohesion, meaning they should do similar tasks, like within one module, functions should operate on related tasks, and they should have a minimum number of entry nodes which do input sanitization in a form. Then once you can decompose them into modules, try to group them into externally accessible and internal functions. That should be relatively easy. And then the difficult part, separate the data structures into the ones that are used for external communication and internal communication. Yeah, I really don't know how difficult this is. And I really have no clear idea on how to do this. A few ideas that are like the first thing that comes to mind over beers is you could calculate a dominator tree on the call tree, or on the call graph. A dominator tree means that if one node dominates another in that tree, like if one node is a direct predecessor of a node, all paths through the second node have to pass through the first one. Which basically means that a dominator tree should be able to identify your gateway nodes in the call tree, in the sense of, if I have an entire module here, and that is only accessible through this function up here, then obviously all these functions down here will be grouped in the dominator tree beneath that function. So basically, I'm not sure whether this will work, but one could try to just calculate a few dominator trees at different points in the call graph, and then take those nodes with a very high out degree and declare them to be gateway nodes to a module. Don't know whether that'll work. Second idea would be try as an optimization problem. You have the entire call graph, and you want to decompose this now into strongly connected components with a minimum number of nodes that you would need to cut away to separate them. The idea behind this is, if you have the big graph, the interface nodes, the external nodes, if you cut them away, you would have disconnected modules, right? So let's try to find the minimum number of nodes that you would need to cut away to separate these things into coherent modules. You probably want, I don't know whether that'll work, just might be an idea. Next idea would be to try to group functions by usage of the same data structures. Meaning you would look at the set of functions, operate, like you would iterate over all data structures in the executable, and look at the set of all functions operating on a certain data structure. And then you would try to create a subset of the executable that has the largest number of common data structures in it, like encloses the largest number of these data structure subsets, and at the same time minimizes the number of nodes in that set. Might work, don't know. Really no idea how this works. Whatever you do there, you probably want to have a parameterized algorithm, meaning something that you can tune, and this is really fuzzy, like this is not hard science. But yeah, I don't know. It's going to be interesting to see whether anybody comes up with anything. All right, challenge number 4. Now we're getting back to the easy stuff. Recovery of template-generated code. Now what's templates really? Templates basically allow you to write code that generically operates on a data structure which exhibits certain properties. And templates are essentially something that the preprocessor will run through. Before I start on going this, I have to tell an amusing anecdote from a German programming contest for, like the German magazine CT had a programming contest where they had some mathematical problem that they wanted solved, and they said whoever writes the program with the least running time wins some cash prize. And some guy submitted a C++ program that would abuse the template syntax and the template preprocessor to solve the problem on compile time and then just output the result. So compile time was something like 14 hours, and he got disqualified, unfortunately. I don't know why. I thought it was a very, very cute thing. So what are templates really? Templates generate for each, like everybody knows STL list, right? So STL list can have whatever data type inside. And this works similar for basically all templates, that for every instantiation of a template with a certain type, the preprocessor just will generate full copies of the original code with the type replaced wherever you had like the template capital T thingy. So you'll generate exactly the same code, just operating on different classes many times. So the compiler is generating these huge amounts of code, and the reverse engineer has to wade through 300 times the same function, which only differs in offsets when accessing the classes it's operating on. So the challenge here would be detect functions that are the same, except for changing some offsets when they're operating on classes. And that should not be too hard. I think in most cases that should be relatively easy. I don't know, it might work with bindiff style algorithms, it might work with something on a semantic level better, I don't know. All right, now challenge 5. This is my favorite, and if you want to think about problems that are really, really hard, this is probably one of the hardest you can think of. Given a location T in the executable that we want to reach, and an executable S in the executable that we can already execute, try to automatically craft input so that T is executed. And scenarios where this would be useful is if you have a static analyzer that finds you bugs, you would like to have a program that automatically triggers them. And if you have something like bindiff that the vendor is patching things, you would still not want to spend days trying to reach that code location. You'd like to automate this. And there's other reasons for this. You would like to be able to improve automated testing by improving coverage. It's solved if you can solve this. Now, to make the entire problem a little bit more interesting, we're not looking for one input to reach location S. We're looking for a description of the set of all possible inputs to reach location S. Because, well, what good is it if we have one